In this video we're going to talk about the unit circle. A unit circle is a circle with center 0, 0 and a radius of 1, as shown in the diagram on the left. Now let's say we choose a point on the circle, x, y, in the top right quadrant, and we draw a radius line to it, as shown just here. Now we draw a line that's perpendicular to the x-axis to that point, and we have a right angle triangle. What we can also then say about this right angle triangle is the length of the sides. So our hypotenuse is length 1, and our side over on the right goes up from the x-axis y amount. So this is going to be y in length. And our bottom line on our triangle goes out x length, so it's just going to be x in length, like that. Now, if we focus on the angle formed between the x-axis and the radius line, we can work out the sine of the angle and the cos of the angle in terms of x and y. So, sine is opposite over hypotenuse, and the opposite in this case is y, as we can see. And the hypotenuse is 1 because it's a radius line. So the sine of our angle in this case, our sine theta, is going to be equal to y over 1, which is just y. And the cos of an angle is adjacent over hypotenuse. The adjacent in this case is x, and the hypotenuse is 1 because it's a radius line. So the cos of our angle theta will just be x. With that in mind, we can rename the point we chose on our circle as cos theta sine theta. And this convention will work for any point on the circle when we measure theta counterclockwise from the positive x-axis. But rather than using that to find points on the circle, we can use it to find the sine, cos, and tan of angles using known points on the circle. The points where the circle crosses the x-axis, so 1, 0, 0, 1, minus 1, 0, and 0, minus 1, can be used to get the sine, cos, and tan of 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So, looking at our two diagrams here, we can use this information to fill in the table on the right. So, for 0 degrees, we're going to be looking at the point 1, 0, which will mean that the cos of our angle is going to be 1, and the sine of our angle is going to be 0. For 90 degrees, we're going to look at the point 0, 1, which means that the cos of our angle is going to be 0, and the sine of our angle is going to be 1. For 180 degrees, we're rotating all the way around as far as the point minus 1, 0, which means the cos of our angle is going to be minus 1, and the sine of our angle is going to be 0. For 270 degrees, we go all the way around as far as 0, minus 1, which means that the cos of our angle is going to be 0, and the sine of our angle is going to be minus 1. And for 360 degrees, we rotate all the way back to the point 1, 0, which means it's going to have the same sine and cos as 0 degrees. So the sine of 360 will be 0, and the cos of 360 will be 1. Now for the tan of all of these angles, we need to remember that tan of an angle is equal to the sine of an angle divided by the cos of that angle. So looking at our table here, we can fill in the tan line. So tan of 0 degrees is going to be 0 over 1, so that's just going to be 0. The tan of 90 degrees is going to be 1 divided by 0, but since you cannot divide by 0, it means that 90 degrees does not have a tan, so that is undefined. For 180 degrees, it's going to be 0 over minus 1, which will just be 0. And for 270 degrees, it's going to be minus 1 over 0. But again, we cannot divide by 0, which means that's not going to have a tan, so it'll be undefined. And 360 degrees, as we said before, is just going to be the same as 0 degrees, so the tan of it will just be 0, like that. We can also use the unit circle to find the sine, cos, or tan of any angle between 0 degrees and 360 degrees, or to solve trigonometric equations where we are given sine, cos, or tan of an angle. We must solve for the angle. So let's have a look. Now, for this purpose, the unit circle is divided into 4 quadrants, starting on the top right and going counterclockwise. So our first quadrant is just here, which means our second is over up to the left of it, and then our third quadrant and our fourth quadrant just in the bottom right, like that. Okay, in each of these quadrants it is possible to figure out whether the sine, cos, or tan of an angle formed by a radius line in the quadrant and the positive x-axis, rotating counterclockwise, is either positive or negative. So, for example, the angle shown in the diagram on the right here is in the second quadrant of the The coordinates of the point of contact of the radius will have a negative x value and a positive y value. So this point just up here. So that means that the cos of angle theta will be negative. The sine of angle theta will be positive, and since tan is equal to sine over cos, the tan of angle theta in this case will be negative. If we look at the circle like this, we can see which ratio will be positive and which will be negative for each quadrant. We can also see whether the x and y values of a point in each quadrant will be positive or negative. So in the first quadrant, both x and y for any coordinate in this area will be positive. In quadrant 2, any coordinate in this area will have a negative x value and a positive y value. In quadrant 3, any coordinate down here will have a negative x value and a negative y value. And in quadrant 4, any coordinate will have a positive x value and a negative y value. So putting that together, we can see that in quadrant 1, all of the ratios will be positive. In quadrant 2, only sine will be positive. In quadrant 3, only tan will be positive. And in quadrant 4, only cos will be positive. So from the first to the fourth quadrant, the positive ratios can be figured out by remembering A, S, T, C, all sine, tan, cos. The other thing we need to know about to use the unit circle to find the sine, cos, and tan of an angle, or to solve trigonometric equations, is reference angles, often referred to as related angles. If we look at the diagram, the angle B is formed from a radius line in quadrant 1. Looping all the way around there, you can see that. The line in that line also forms an angle A1 with the x-axis. So we can see A1 just marked just here. Also in this diagram is another radius line forming the angle A over on the right. The radius lines drawn here connect to the circle at the same perpendicular distance from the x-axis as each other. In other words, the points will have the same y value. This will mean that the triangles formed by the radius lines and the x-axis will be identical. So the angle formed with the x-axis and the hypotenuse of each triangle will be equal. This angle A1 is what we call the reference angle for angle B, and we can use it to find a value for sine, cos, or tan of an angle measured from the x-axis counterclockwise. This diagram shows this all together, and you can see that the reference angle in each quadrant is always the acute angle formed with the axis. So if we imagine our angle coming around from our positive x-axis to each of these points, we can see what our reference angle will be. In quadrant 1, we don't really use a reference angle because we would just be measuring the actual angle itself. In quadrant 2, our reference angle will be theta, which means our actual angle will be 180 degrees minus theta. In quadrant 3, we can see that our actual angle will be 180 degrees plus theta. And in quadrant 4, we can see that our angle of rotation would be 360 degrees minus theta. So that's how they would all work out. Okay. So let's just see an example of this. In this problem here, we have to find sine 240, leaving our answer in surd form. So the first thing we need to do is we need to figure out our reference angle, which is marked in the diagram here as theta. So our reference angle for 240 is going to be 240 minus 180, the difference between our full rotation and a rotation just as far as the x-axis. So our reference angle theta is going to be 240 minus 180, which is equal to 60 degrees. So that is our reference angle. Now what we're going to do is we're going to get the sine of our reference angle since we've been asked for sine. Now, from our tables, we know that sine of 60 is root 3 over 2. And then using the ASTC rule, we know that angles in the third quadrant have a negative cos and sine. So the sine of 240 will be the same as the sine of 60 degrees, but it'll be negative. So our sine of 240 degrees is going to be minus root 3 over 2. Similarly, we can solve equations like this. So we're being told that the cos of theta is equal to minus 1 over root 2, and 0 degrees is less than or equal to theta is less than or equal to 360. In other words, our angle theta in this question is between 0 and 360. Now, our calculator will tell us that the cos inverse of minus 1 over root 2 is 135 degrees. But that's not the full answer. To solve this, firstly we need to ignore the negative sign on the fraction. So we just start off by saying that cos theta is equal to 1 over root 2, like that. Then we could use the inverse cos to get theta. So we would say theta is equal to cos inverse of 1 over root 2. And we would find from our tables or our calculator that in this case, our theta is going to be equal to 45 degrees. But this is our reference angle for our solution. Then we got to consider the 4 quadrants. You can see this over here on the right. Cos is negative in quadrants 2 and 3. So, with our reference angle, 45 degrees, we can use that and sketch our actual solutions out like these two diagrams just here, where the green angle marked in each one is 45 degrees. So the solutions to our problem are going to be on the left 180 degrees minus 45 degrees, which is 135 degrees, or on the right it's going to be 180 degrees plus 45 degrees, which is equal to 225 degrees, which means our angle theta is going to be equal to 135 and 225 degrees for the solution for that. So that was a look at the unit circle and some of its uses.